Here we'll see how the inertia of a fluid going through our pipe is going to be analogous to an inductor in an electrical system. So if I have a segment of pipe that I want to look at that has fluid going through it, making our pipe first. All right, so I have some segment of fluid inside this pipe that's going to be traveling, let's just say, left to right. I'm going to have some length that the fluid has, and then the pipe is going to have some cross-sectional area, which I'll call A. And I'll note that this derivation is only for prismatic pipes, so a constant cross-sectional shape as I go left to right. If we have a narrowing pipe or an expanding pipe, the derivation for the fluid inertia is going to be different for that case. So let me take out this little piece of fluid and see what is happening to it. Right, so our little piece of fluid is going to have some pressure acting on it on the left. I'll call it P sub L for left. And it's going to have some pressure acting on it from the right. I'll call P sub R. Now, these are pressures, so if I want to draw, let's say, a free body diagram, I am going to need to see on what cross-section these pressures are acting. So let me get this into a little bit more of a 3D shape. So it's going to be the pressure times the area, assuming uniform pressure across the surface of the left side and the right side. Again, it's constant cross-sectional area, so the A's are going to be the same on both sides. So those are the forces acting on this little segment of fluid, and that will be equal to, well, the inertia of the fluid. So let's establish some coordinate system here as it's developing into a free body diagram. So if x is going to the right, then the inertia is going to be the mass of the fluid times its acceleration. So the left-hand side are, again, the forces acting on this little isolated cylinder or prismatic solid of our fluid, and the right is its inertia, its mass times its acceleration. So let's get an equation out of this. Well, if I sum forces in the x direction, I am going to have this PLA minus PRA equals mx double dot. And I can factor out an A and rewrite it this way. And now I am going to say that there is a pressure difference, I'll call it delta P here, times A. So PL minus PR, I'm going to call delta P. Delta P could be positive or negative, as could the x double dot. So I'll just call it delta P is the left pressure minus the right pressure, equals mx double dot. Now I can do a little bit of manipulation of how I am expressing some of these variables. Instead of x double dot, well, x double dot is the acceleration. I could also write that as the rate change, time rate change of the velocity. So dv dt. Acceleration is just the time derivative of velocity. So I've just rewritten it in a different way. And I can make another adjustment on the next line. So the mass of this little plug of fluid is going to be its density times its volume. Well, its density I'm going to say is rho, and its volume, because it's prismatic, is going to be its area times, in this case, its length. So I can rewrite this as rho AL dv dt. So I haven't changed anything, I'm just rewriting x double dot as dv dt, and the mass as rho AL. Again, this is where it only works for prismatic pipes. I'll rewrite or rearrange this just a little bit. I will have rho and L, and then I will group A and dv dt. So the area times the velocity, or sorry, the acceleration of this fluid. Well, this a dv dt, thinking back to fluid dynamics you have seen before, and oftentimes we were calling this q dot, which is dq dt, if we want to write it that way. So a times dv dt I can now rewrite as the change of the volumetric flow, or the derivative, the time derivative of that volumetric flow. So a dq dt I'll write it that way. So now, where are we getting? Well, we have a P in the equation, we have a Q in the equation. Again, what we're looking for these elements is the relationship similar to what we saw in the electrical systems between the voltage and then some impedance and our current. We're going to have a pressure and then the equivalent impedance, and then our current is going to be our volumetric flow rate, our Q. So this is the form we are trying to get into. So we're almost there. At this point, the delta P, again, the change in pressure, I am just going to refer to as P, but we know it means the same thing. And I can divide through by that A, and then I have this dq dt. Now I'll take the Laplace transform of both sides. So P will go to fancy P. Again, this is a function of S because pressure was a function of time, equals rho, L, and A are constant in time and therefore are not affected by the Laplace transform. And we have a dq dt or a q dot. Either way we would want to express it, we have a time derivative of q. Well, thinking back to Laplace transforms, to do a derivative in the Laplace transforms is the same as multiplying by an s. So that is the same as s times capital Q. This looks like in the electrical world the relationship for an inductor, that the voltage was equal to this Ls times the current. So what we are looking for is going to be, what's the equivalent inductance? Well, it's going to be fairly straightforward. When we look at this, we have this rho L over A, and now that is going to be in this same form. So bringing this out, this is telling us that the equivalent inductance for the fluid inertia is going to be rho L over A. So if we need to model the fluid inertia, we can model it like an inductor or as an inductor when we go to draw our equivalent circuit diagram for the fluid system. Now let's take a quick look at this relationship. The denominator here is that cross-sectional area of the pipe. What we're going to see is the larger that area is, the lower this inductance is. So for sufficiently large pipes, that is ones with what we'll call large cross-sectional areas, this L is going to be relatively small until the point that usually it's going to be neglected. Now, the definition of large is nebulous. What is a large cross-sectional area? Well, it depends on the system that we're looking at. But in large-scale pipe systems, we will typically ignore the inertia of the fluid because A is going to be relatively large, so L is going to be small. But in small systems where we have a narrow cross-sectional area, now the fluid inertia we probably don't want to ignore, and we're going to put the inertia of the fluid itself into our model. So the pipe, which again is analogous to the wires in the electrical system, for narrow or small diameter pipes will not act as just a wire. It will also have some inertia in it that we are going to be compensating for.